Hey guys, so I want to make this AP Physics 1 review for Unit 2 for y'all. I was gone over the state meet, so I just wanted to give y'all some quick tips to how to succeed on this test. And this test, I'll tell you now, it's not going to be extremely intense trig or anything, but there's a few things I think should be useful for y'all to memorize just to work through problems fairly quickly. So the first thing you should know is your formulas that may or may not show up. F net's equal to MA. You for sure need to know this one. It's kind of on your equation sheet, but you should just memorize it ahead of time. You should know that FG is equal to MG. And let me break this up. And I've noticed this has been kind of an issue. FG sometimes is written as W because it is your weight, which is the force of gravity. So all of these they mean the same thing. Weight, force of gravity. This is just how hard, essentially, a planet is pulling you. For our case, it's Earth is pulling us with this much force. Mass is the amount of matter that an object contains. Your weight changes depending on how far away you are from, the Earth. Your mass does not change. If we're on Mars, we have the same mass, we have a different weight. And then little g is gravitational field strength. And the problem I keep running into is that I say, someone's like, what is gravity? And some people will say F sub g. Some people will say g. G is gravitational field strength. And it's the product of M and G that gets you your weight. So just be careful about if you see wording, if it's weight or force involved, it's F sub G. If it's mass, it's M. If it's G, it's gravitational field strength. When we refer to M over here, it's this M, right? They should be the same M. So if we're dealing with orbit, those are the M's we're talking about. It's this FG as well is only local FG, not like universal FG. If you need the universal one, that's where you have to use the big equation over here that you can find on your equation sheet. So I just want to clear that up. That's an important one to go over. If you're given, let's say someone is 400, their FG is 400 newtons. First off, all forces are newtons. So if you see a newton, it's a force. If they're referring to how heavy someone is, they mean F sub g. So anyway, someone's 400 newtons. I should be able to pretty quickly go, oh, they are 40 kilograms. How do I get that? Fg is equal to mg. Assuming we're on Earth, 400 is equal to 40 times g. So g is 400 over 40, which would be 10. I always know that G is equal to 10 newtons per kilogram, so I can always, I always have this as a constant if I'm on Earth. So whatever your weight is, divide by 10. Whatever your mass is, multiply by 10. A lot of people, they're using F nets equal to MA, and they will be given the mass, and they'll plug in the weight for M. You gotta clear those up. You can't mix them up. It's gonna make a lot of these problems coming up very difficult on this test. This test will give you sometimes the mass, sometimes they'll give you the weight that you have to find out the mass from. So you gotta know that. Moving on, there's some scenarios that always seem to pop up in this Unit 2 test. The first is just objects on a ramp. And you don't need to know how to derive this, but just know that the force diagram here would be FG's going that way, FN's going this way, FF is going this way. So this is FG. If there was a horizontal line here, this would be theta, this angle would be 90 minus theta, this is your FN, this is your force friction, and you end up making a triangle that's always something along these lines. This is FG, this is FN, this is FF. This angle here is always theta, and what you always end up getting is Fn's equal to Fg cosine of theta. Now, this is the scenario where we're somehow balanced. If we're unbalanced, generally we're sliding up or down the ramp, and depending on that, that would form some sort of gap here, or maybe if you're accelerating upwards, that's where your net force would be. But this is a useful equation that pops out. And then this would make whatever length is here, FF would be equal to FG sine of theta. If, let's say, you have a net force, so instead of it actually being a closed vector addition diagram there, you have FG, FN, FF, and then you have a net force. This net force would be going down the ramp. And so now, instead of ff equaling fg sine theta, ff plus fnet's equal to fg sine of theta. So this is something that could pop up. So be careful. Also know, like, this is kind of the ideal scenario, but if you find out, oh, actually a rope is pulling it up, so there's an FT involved, but there's still friction, you have to deal with, now that you're moving up the ramp, FT would be going up. Because motion is this way, friction would be going that way, normal force would be going this way. So there's a couple ways these scenarios change, but you should know, like, this triangle starting to form here. You can pause the video and try to see what this triangle would end up being. Let's say that it is accelerating up the ramp. So what would that end up being? Pause the video, see what you get. I'm going to draw it right now. So FG would be going down. FN would still be going up. FT would be this way. And I'm just going to draw FF. So, sorry, if it is accelerating upwards, it's getting pulled up, we'll say FF is not as long. So FT is this whole long part. FF is the small part. And then you have this FNet here, that's a gap that would be going up the ramp. Because you started here, you end here. So that's the direction FNet is. FNet's the direction of your acceleration. So if you're ever confused about where the gap should be, if you identify the direction of acceleration, that's what it should be. So FNet and acceleration, same direction. This would be FN over here. If I want to draw this, like, FN is still mg cosine of theta. I replace FG with mg. For this whole length here, if I tried to figure it out, like, FT is equal to this part here, FG sine of theta, plus FNet and force friction. If you drew your arrows the right way, then you're probably going to get the signs right. Remember, like, this whole length of FT is equal to this part plus this part plus this part. So hopefully you can see my little pen here. It's equal to those three. This is where you can substitute stuff like FNet's MA. You're given a formula for friction. It's equal to mu Fn. So you can plug that in to here. We know Fn is that. So these equations get pretty long. If it's a multiple choice, it's probably not too bad. But if it's a free response, they may ask you to derive everything. There's no formal equation for Ft. So something like this, you would have to figure it out from there. All right, so that's one scenario, just anything on a ramp. Another one's the Atwood machine. And the Atwood machine works kind of multiple ways. You have, I always give this scenario, and I wouldn't worry about for this test anything at an angle, but it's really not too much different, just a lot more algebra if it's at an angle. Essentially, the quick way to do these problems is treat all this as one system. So if you treat everything as a system, not just separate, then you can just go FNet's equal to MA. If there's no friction, the only force that's really driving this acceleration is going to be the Fg of the hanging mass. So Fg hanging mass, there is an Fg here and an Fn here, but they cancel each other out. So the only thing that matters there is Fg hanging mass. So Fg hanging mass is equal to the mass of, let's call this m and little m. So big M plus little m. And then that would be the acceleration. And that's how you would solve a problem like this. Acceleration would be Fg little mass over big M plus little m. All right, another one, elevators. So if you're a person in an elevator, they ask these questions a lot, and really what it comes, if you are just concerned about the person, there's only two forces on them. There's gravity going down, and there's normal force. And depending on how your motion is going, that's going to determine how your net force is. Acceleration is going to be, or let me set up this whole problem. Fnet is the difference between Fn minus Fg. If you are not moving or constant velocity, if you're balanced in some way, your F net's 0. So that means your Fn's equal to your Fg. That's just how it's going to work if you're balanced. Your elevator can be moving and balanced, so you need to watch carefully for what it is. Now, if you have a positive acceleration, that must mean the floor is pushing up more than your weight. So Fn must be greater than Fg. When we talk about the motion of a person in an elevator, there's kind of 6 scenarios we think about. There is, you start moving upwards, you go constant velocity, and then you slow down to the top. Then we get, you start moving down. When you start moving down, you accelerate downwards. Then you go constant velocity, and as you approach the bottom, you accelerate upwards. Note, in this scenario, you're slowing down. You're speeding up, slowing down, speeding up. So in this scenario, we must have a positive acceleration. In this scenario, we must have a negative acceleration. In this scenario, we must have a negative acceleration. In this scenario, we must have a positive acceleration. Logically, if you can check how you would feel in an elevator, if you would feel heavier, that means you have a positive acceleration, it means your Fn's greater. If you feel lighter, then that means your Fg must be greater. It must mean that your Fn is not actually pushing up on you as much, which is what happens towards the top. The bottom, the elevator has to do more work. The top, you can let gravity work with you. That's roughly what's going on here. So just, every scenario, just draw a quick little force diagram. These are super simple ones in the elevator. You just have to keep your mind wrapped around what's going on. So let me check my time. All right, 12 minutes. We're doing good. Circles. Let's talk about circles. So wherever you are in a circle, let's say we're spinning counterclockwise, so counterclockwise, your velocity is tangent to whatever moment you're going, and you have some sort of centripetal direction of Fc. It's also the direction of your A sub c. Your Fc is a net force. So you do have some sort of net force. Just a clarifier, let's say I'm spinning a circle, I'm spinning an object, it's attached to a string in a vertical circle. Vertical circle, ball attached to string. And it's gonna go this way, let's say. The forces on this object is you've got Ft here, but it doesn't mean you don't have an Fg. And so you can have essentially this part, which would be an acceleration in the tangential direction and an acceleration in the centripetal direction. I know these T's are kind of confusing, but this is tension. This is tangent, just so we know the difference. You could still have them. You just need an acceleration in the centripetal direction to go in a circle. The next moment in time, you're going to still have a tangential velocity and a tension, but that is, you could still have the circular motion. So as long as you need to have a centripetal acceleration to move in a circle, that doesn't mean you don't have other kinds of acceleration directions. The most common one we'll see is gravity. Object floating around, it's traveling around, there's some sort of planet. This is the R. It's not to the surface of the planet. It's all the way to the center of the planet. It's the R. Fg. So this is Fg. Fg is equal to m1, m2, big G over r squared. m1 would be like this object. m2 would be the big planet. I also have Fc is equal to mv squared over r. The m, because you're probably concerned about this object that's actually doing the circular motion, would probably be m1. be comfortable with saying FG is equal to FC, relating them, and I'll write it out down here, M1, M2, big G over R squared equal to M1 V squared over R. M1's cancel, R's cancel, and you'd be left with M2 big G over R is equal to V squared. So if you need velocity, this is where it can pop out in orbit. Another one they like to ask is, what is little g? We did this little practice of how we found our Earth's little g. You can always do that if you have the Earth physical constants, but you can say this FG is equal to the big FG. Remember, this would be M1 as well. Relate them, big G is equal to FG is equal to FG, M1G is equal to M1, M2, big G over R squared. These M1s cancel, little g is equal to M2, big G over R squared. This M2 and this V, both of them rely on pretty much the same stuff, which is big G, which is a constant, that's not going to change. M2, the mass of the planet or the thing causing the orbit, and then how far away you are from the center, the R. It doesn't matter on the object's actual mass, like the satellite's mass. It does not matter for that. It would only matter if it was so massive that it caused like a change in like the planet's orbital mass, which won't happen unless it's like 2 stars. What your own mass does matter is your actual FG. So if you need to find your actual FG, you do need to know your mass, whether it's that equation or the big equation. So that's the only time your mass actually matters, your own weight. If it's about what you need to do to orbit something, it's the other objects that matter. So far, we've talked about ramps, modified Atwood machines, elevators, circles. The circle stuff, just like orbit's gonna be the most common one, but just know like you gotta be able to make a force diagram whatever happens. So okay, I do want to give y'all just another reminder. If you're given something weighs 80 newtons, you see 80 newtons, they tell you it weighs, or the force of gravity is 80 newtons, you can determine that that's about 8 kilograms. Because G is equal to 10 newtons per kilogram, and FG is equal to mg. I can't emphasize enough, if you know the weight, and you know you're on Earth, you know its mass, and you know how to get there, the conversion to little g. So the conversion for mass is divide by 10 if you have the weight. If you have mass, multiply by 10. So that's how they're related. So there's that, and probably the last thing I want to go over is, let me look at. The last thing I just want to mention is just a clarification on all of Newton's laws. Sorry if there's a pause there. I was just making sure I covered everything else before I get to this point. I'm going to type them out just so we can see them. So Newton's first law, it's called the law of inertia. And it's the basic concept that if there's more mass, it's harder to move. That's the... an object at rest will remain at rest unless touched by a unbalanced force. Newton's second law, F net is equal to ma. This is the one, like, you use this all the time. Even if it's balanced, you're just saying your acceleration is 0, so your F net's 0. And Newton's third law, equal and opposite. You know, AP questions, they don't ask Newton's third law questions that much, but you need to keep an eye out for, hey, if one object is touching another object, what is its magnitude? And it should be like its equal magnitude, opposite direction, something along those lines. It's the way to identify a Newton's third law question. They're asking about the exact same force between the exact same 2 objects. If there's more than 2 objects involved, if they are different forces they're identifying, they are not talking about Newton's third law. In a force diagram, you are not going to see the Newton's third law pair. You need at least 2 diagrams. I'll give you an example. There is a block on a table, and that block has Fg, and that block has Fn as well. So these are the forces on this block right here, right? From the Fn's from the table, the Fg's from the Earth. That's what's causing it. Some people will say this is an equal and opposite reaction. That is not true. The way I would see this equal and opposite reaction is if I had a table and I could draw what forces were acting on it. But what I'm going to do is I'm going to add another block. So I'm going to add another block. You know what? I'll draw it over here, just so, draw it below here, just so we have some room. So I add this red block here. Now, what I have on this object is I have FGE. This is the weight of block 1. And notice I kind of drew them the same size. I have now object 2. So, I'm going to put this Fn caused from object 2 touching object 1. So I'll call it Fn2. And then I have this Fnt. What you'll notice is this Fnt grew larger than this Fnt. The Fg1 is the same size over here because the interaction that changed is not with this block in the earth, it was this block with the table. So I'm showing all this to show you, like, what is my actual Newton's third law pair. Well, I can find one of them if I draw this force diagram over here. This is Fg object 2, and then we have Fn from object 1. Well, it turns out that what I'm referring to here is 1 and 2. These normal forces here, this is a Newton's third law pair. So see, it took me 2 force diagrams to show you this was the Newton's third law pair. These could never be a Newton's third law pair, even though they are equal and opposite in terms of like their value. This is an Fn, this is an Fg, this involves the table in block 1, this involves the earth in block 1. There's 3 objects involved. These can't be a Newton's third law pair. Versus this one, they're equal and opposite. It is objects 1 and 2, 2 and 1. So the same objects, same normal force. That's why these are a Newton's third law pair. So just be careful. These questions can pop up. Usually these questions are there, but they're like you're drawing a force diagram, you're doing something else. It's like part of a bigger part of the problem, but sometimes you will get very direct Newton's third law problems. And that's pretty much all the things I think you should worry about. Just be familiar, like do practice problems. You can make your own problems, or you can look them up of any problems on a ramp, anything with a modified Atwood machine, these elevators. One last thing, if you're ever given a force at an angle, you have to be comfortable using the trig and being able to split it into different parts. This is the actual force. You break it up into components because it's easier to deal with components. A lot of times you'll have something like a block being pulled this way, and the problem is that it's accelerating this way, so the acceleration's that way. So your Fnet is also in that direction, but you need to know how to split this up. Well, if Fnet is in the x direction and acceleration's in the x direction, I need to get all my forces in the x direction, and so usually there'll be like a friction force, a normal force, a gravity force. So force applied in the x direction minus force friction would be equal to the a of x times whatever the mass of this block is. So that's how you would solve a problem like this. You'll notice that like F net y is 0, so FAY minus FG would be equal to 0, and that's how you work this problem. Sorry, FAY minus FG plus normal force. Plus normal force is equal to 0. So that's how you work those problems. So be comfortable with trig. In this context, I would say if you need like 80 lines of trig, like in a problem, don't worry about those. I'm not going to hit y'all with that hard of problems for this test. Maybe later on I might give you a harder question like that, but the AP tests aren't too algebraically, they try not to make them too algebraically difficult. It's a lot more logic with it. So that's what I've got, and I'll see y'all in class.